Hi guys, welcome back to Data Every Day. Today we are looking at a data set of images, actually drawings of squares, circles, and triangles, and we're going to be trying to guess what shape is present in the given image. So there's 100 of each. We have 100 circles, and you can see. Actually, having a hard time seeing this. So let's open it up. You can see they're 28 by 28 grayscale drawings of shapes. So we're going to build our own CNN, convolutional neural network, to try to classify these. So let's hop into the notebook. We're going to be using NumPy and pandas for working with the data, as well as the path object from pathlib and the os.path. Then for pre-processing, we'll use the train test split function from sklearn, and for loading the data and building the model, we'll use TensorFlow. Before we get started, I'm going to go ahead and enable GPU acceleration, which will speed up the training time of our CNN. Alright, so once that loads up, let's now import everything. And when we've done that, the first thing we want to do is go to the data and get the directory path for the folder that contains all of our class folders. So these are the class folders. Within the class folders we have the actual drawings, and we're going to get the path to the parent folder of those class folders, so shapes. So I'll call this image_dir, and actually it glitched out there. Just put in shapes. That is the path, and let's turn it into a path object from pathlib, and you'll see why in a second. Alright, so I'd like to create a file data frame. So when you have this format of your directory with the images, when you just have one directory with the class folders and the images inside, unfortunately the image data generator, which is how we load in the images, does not allow for 3 splits in such a format. What I mean is, let's say we want a train split, a validation split, and a test split. Unfortunately, we won't be able to do that using the flow from directory function. So if we want to be able to make 3 splits like that, we're going to need to create a file data frame, and we're going to use flow from data frame instead. So file data frame has to contain on one column the locations, the file paths of each image, and another column that contains the label for that image. So let's go ahead and get those 2 bits of information. First we can get the file paths by taking our image_dir, which is a pathlib path object, and using its glob function, which allows us to use a glob expression to search for files within the directory tree. So let's find anything followed by something.png. So if you look in here, these are all PNG files. The double star means go through directories. Just recursively search through all directories until you find something that ends with PNG, and then return all those file paths. So we can turn that into a list to get the actual list of file paths, and you can see here they are. This is the file path to every image in our shapes folder, regardless of which class it's in. You can see we have squares here. Up above we have circles, and at the bottom we should have triangles and squares again. Okay, so let's put this into a data frame. So what I'll do is call this file paths. Now before I here, let me do this. Before I actually turn it into a data frame, I want to notice that the label is actually contained in the file path. So we can extract it's always in the same format too. It's always the parent folder of the file name. So we can extract this using os.path. If we use the split function from os.path and pass in one of these paths, it will split the file name off from the rest of the path. We can then just target the first element of this split to get back the parent directory, and we can split it again to split the label name off from the rest of the path. Then we take the second element, and this will return us the label name. So what I want to do is apply this function to every one of these file names, file paths. So what we can do is replace this string with just any x. We'll call x one of the file paths. And we can make a lambda function that's going to map every x to this thing. and that will just take a file path and return the label contained within it. So this split function works on both strings and on path objects, so we won't have a problem here. Let's take this function and use it up here. So we're going to create a map that's going to map the function to file paths. Then the map we're going to turn into a list, and we're going to store the result in labels. Alright, so let's see how this goes. Labels should not be a list of all the labels and in the same order as the file paths. So if we now go and make a data frame out of it, first what I want to do is turn them each into series objects. We don't have to do it this way, but I'm going to. So we take, we'll just use the series initialization function, pass in file paths, and then rename file paths, like so. And then in here, let's give it a name. That'll be the column name, which will be file path. Then we'll do the same thing for labels. Pandas.series of labels. The name is label. Only thing now I need to note is that the file paths are actually path objects, and when we use TensorFlow to load the images, it's going to require that they're strings. So I'm going to now convert it into a string column with as type string. Last thing to do is take the image df. We're going to create an image df by using pandas.concat to concatenate together the file paths and the labels side by side. So access one. Let's take a look at that. And there you go. So we have the file path and the label for every one of these 600 images. So there's 600. How can there be 600? Shouldn't we have 300? There's 100, 100, 100. So maybe something is wrong here. This is a bit suspicious. We should only have 300 here. So let me just take a moment to try to figure out why this is. Okay, I inspected it. It seems to be a problem with Kaggle's directory system. If you look up here, when we actually load in the file paths, you'll notice we have some of the images are actually contained in a second shapes folder within the first one. When we look up here, we can't see any second shapes folder, but there seems to be a duplicate of the folder within it that we can't see. So we can fix this. You'll see this is returning 600 rows when it should be 300. If we just search for all images within shapes /shapes, so if we go into that second folder and then run this, you'll see it's now returning the 300 as it should. So that fixed it. So last thing I want to do is actually split the data frame with the train test split function. So I'm going to create two new data frames, train.df and test.df, using the train test split function from sklearn. We're going to pass in image df, give it a train size. Let's have it 70%. Keep shuffle equals true, and give it a random state. So this will shuffle the data frame before we make the split, and the random state ensures the shuffle is always done in the same way. So I guess we could just take a look at both of these. So train.df is just 210 of the rows, that's 70% of the original data, and you'll see it's been shuffled. Test.df is the other 30%. So we really don't have too many images here, so we'll see what kind of results we get, but we don't have too much data to work with. Alright, let's do loading image data. So now I'm going to create the generators. The reason we use generators is, well, it's really not such a problem with this dataset. Because we have such little data and each image is quite small, we don't really need to use generators. We could actually open each file individually and store it all in memory, and that should probably be fine. But the problem arises when you have either large files or a lot of files, or both, in which case you can't load them all into memory at once because you'll run out of memory. So the generator loads them in batches, trains on them, and then recycles the memory afterwards for the next batch. So we're going to make some generators, and that comes from tf.keras.preprocessing.image.image.data-generator. And let's call the first one train generator. So inside the generator initialization, we can include any sort of data augmentation or pre-processing steps we'd like. The only one I'm going to do is rescale. So we can rescale by a factor of 1 over 255. Sorry, 255. And this will have the effect of scaling all the pixel values between 0 and 1. Because the maximum pixel value is 255. So if we divide all the values by 255, it compresses them down to that range. I'll also give this a validation split because I want to draw my validation images from the same generator. So let's say 20% goes to the validation set. Alright, then we'll copy this over and I'll make a test generator. This one will not have a validation split, but it's the same thing otherwise. Alright, now we'll use the generators to load the images. So when we're loading them here, we're not actually loading them into memory, we're just like creating a specification for how to load them when we do the training. So let's use train generators function, flow from data frame. So here we specify the data frame that contains the file names and the labels, and that would be train.df, which we created earlier. We specify an x column, which is the file path column, which we called file path, and a y column, which is the label column, which we called label. Then we should pass in a target size, which is what do we resize the images to. So we're already working with really small images, as you saw. I think they're exact. I measured it. They're actually all 28 by 28. So we're not going to resize them. We're going to leave them as 28 by 28. The color mode. So this is how many color channels do we have. As you saw, they're grayscale images, so we just type grayscale. Then the class mode. If you're just doing two classes, this is binary. Otherwise, it should be categorical. And then we'll give it a batch size. So if we could declare the batch size here, we don't have to do it later in our fit function. Let's do 32 batch size. And shuffle equals true. Since this is a train set, we definitely want to shuffle. And let's give it a random seed as well, so that we can reproduce it. And then the last one, which is important, is subset. Subset, you can only use this if we are using a validation split. This can either be training or validation, and this just says whether to take the 80% or 20% based on the split. If we do set a seed, the subset will always be drawn in the same way. So if we're gonna take, which we are, you'll see we're now gonna flow the validation images through as well. And if we're taking both sets, we need to make sure the seed is the same so that we get the same, we have overlapping data. Alright, so we're going to flow for the data frame here and flow it into train images. So you can think of this as having the actual image data, but it doesn't actually have the image data stored in it. It just has the specification for how to load the image data. This here we'll call val images, and this is the validation data. So let's copy it over one more time to create our test data set. This is test images, but this doesn't come from our train generator, it comes from our test generator. So let's change that here. And we're also flowing from test.df instead of train.df. Last change is that we're not going to need the subset or seed arguments, and the shuffle should be set to false, since we'll only be evaluating this data and not training on it. Alright, let's run this then. And you can see how many files it found for each set. So this is our train set, our validation set, and our test set. Okay, so we've loaded the data, or we've specified how to load it. Now let's build the model. So I'm going to create a convolutional neural network. The idea behind the CNN is to extract features from the image that are useful in making predictions, and then turn those features into a sort of consolidated representation and use that representation to make predictions in the normal neural network method. So we'll start with an input layer. This is tf.keras.input. The shape here is going to be the size of a given image, and this will always be 28 by 28 by 1. The 1 is for the single color channel. Then we'll create our next layer. I'll just call the layers here from here on X, and this is going to be a conv2D layer. So the convolutional layer is going to look at the image, which which is two-dimensional. Technically it's three-dimensional, but it works across the first two dimensions. It basically slides a window across the image, the whole image, and it has a set of weights that it slides over, and it multiplies those weight values by the pixel values, adds them all together, and then sends it to a new two-dimensional output. And it adds a new pixel to this new two-dimensional output for each time step that the window slides. So this has a few arguments we need to pass. And I should say that the point of doing this is to extract bits of information that contain spatial relationship data in the image. So we have to specify the number of filters. And a number of filters is how many times do we make a full pass over the image. For each full pass, we're using a different set of weights, and we're also creating a new two-dimensional output. So if we make this 6, for example, this first layer will look at the image and create 6 new two-dimensional features that are created by looking at the original image. We also specify a kernel size. This is 3 by 3 by default, and we'll keep it that way. And finally, an activation function, which we'll do ReLU. So let's pass in inputs to this, and let's take a look at this. So our inputs, we're coming in with a 28 by 28 by 1 image, and then it gets turned into a 26 by 26 by 6 image. Well, you could still think of it as an image, but it's really just, it's uninterpretable at this point. So the reason this goes to 26 by 26 is we actually lose a pixel on each side because of our 3 by 3 kernel or window. So when the window hits the edge, it's not going to go off, so we do lose a pixel because the center of the kernel can't go all the way to the edge. And then the 6 comes from this filters. So we pass over the image 6 times. Each time we create this new, we create a new 26 by 26 output. So what we end up with is 6 different 26 by 26 outputs, and that would be the output of this layer here. So the next thing to do is to pool the information. tf.keras.layers.maxpooling2d. And what this does is it also slides a window across. I think it's a 2 by 2 window by default. It slides a window across this output, and it just takes the max at each time step to reduce the dimension of the image. But what that also allows us to do is put a second convolutional layer over it and sort of extract higher level features. So when we pull it down, it allows the next window to come along and see more of the image at a given time. So what we'll do is copy this over and add a second convolutional layer. This time we're going to extract 16 different features from it. This is a pretty standard setup. But you definitely play around with these to try to get optimal performance. I'm not going to do that today, but this is what we'll stick with. So we start off with 6 features. That gets pulled down. Then we take 16 features from that output. Then we pull it down once more. And then we're going to do an average pooling. So this is not, I think there's an average pooling 2D, which does a very similar thing to the max pooling 2D by sliding across. But we're actually going to do global average pooling 2D. And what that does is it takes the 3-dimensional output of the previous layer and averages across the first 2 dimensions so that we get a single 1-dimensional output. And we do need a 1-dimensional output to move forward. So if we run this and now we look at X, you can see the final output is actually just 16 numbers. So you can think of the numbers that this outputs as sort of features that have been extracted from the image. So we have 16 different features that are coming from the image, hopefully that contain some sort of useful information. Now we use those 16 features to just do a standard classification. So with dense layers, we'll do a tf.keras.layers.dense. Let's give it 64 neurons, a ReLU activation function. I'll pass in X, we'll copy it over. So we have 2 hidden layers, and then we'll have our output layer. This is also dense, but it's going to contain 3 values with a softmax activation. and these will be each one of these three values will be the probability for of classification for a certain class. So we have three classes. Each one of these corresponds to a different class. The highest probability will be the prediction. So we'll pass in x here, and then we'll create our model. tf.keras.model. The inputs are inputs, and the outputs are outputs. We'll compile the model. We'll use an atom optimizer. For our loss function, we'll use categorical cross entropy, which is you actually need to use categorical cross entropy instead of sparse categorical cross entropy if you're using these generators, because it encodes it in a vector form instead of just an integer. We'll just use accuracy as a metric since it's multi-class. And let's store the result in history. So model.fit. We're fitting on train images. Our validation data is, I think it's called val images. And then the number of epochs, let's train for a bunch of epochs, 100, and then give it an early stopping callback function. tf.keras.callbacks.early stopping. So this will allow us to monitor the validation loss. And when it notices it hasn't improved after a certain number of epochs, which we specify here, let's say 3, it will stop the training and restore the weights from the best epoch. Now I'm actually going to bump this up to like 5, I think, because I noticed the training on this is very unstable, probably due to the number of images, small number of images we have. Alright, let's see how this goes. It shouldn't actually take too long since we are dealing with really small images. There it goes. Alright, it finished, but I want to give it a little more time because, okay, you know what I'll do is I'll take off the callback function and just train for 100 epochs so we can see what kind of loss we get after a long enough time period. So it's going up to 40, 47. Oh, now it's, yeah, this is not, oh, strange. It is going into 50 now. So it's looking like it might take some time. Wow, it hit 73 at one point. So this is very unstable training. The loss is jumping around everywhere. When you have such unstable training, it's not a good idea to use early stopping. Instead, what we should do, instead of using early stopping, we'll use model checkpoint. So model checkpoint allows you to save the weights at a given epoch. You could have it save every time, but what we're going to do is we're going to say save best only equals true. That means it'll save the weights from the best validation loss epoch, with the epoch with the lowest loss. And we'll just do save weights only also, because we're only going to use this save to load up the weights again for the same model. Alright, so let's do that. Run this. Oh yeah, we have to specify a file path to save the model. Let's do it in the working directory with model.h5. So h5 is a HDF5 format you can save Keras models as. We're only saving the weight values here. So that's going to run for 100 epochs, and it should save the model's weights when we get the best loss, which looked like it was up into the 70% accuracy. So hopefully we get that again here. But it does seem sort of random. And you know, we really have such a small amount of data to evaluate it on also. I'm not sure if it even got there. Oh, it hit the 64. Okay, that's the best we can hope for. When you're doing model.checkpoint, afterwards you should say model.load weights. We now want to load the weights that we saved. So if you look in the working directory, we have this model.h5. Oh, I don't want to download it. I want to just copy that file path, /model.h5. And that will load it in. So now we should have the weights loaded from whichever one of these had the lowest loss. Oh, was it maybe the last one? It's the only one that went under 1. Okay, so results. Let's just get the loss and the accuracy. So we'll get the results by using model.evaluate on the test images. And I'm going to set verbose equals 0 so that we don't see the loading bar. Then we're going to print out the test loss. Let's display this to 4 decimal places. And then format this using results sub 0. So results, this model.evaluate will return the loss of the accuracy. The first element is the loss. Copy this over and get this, oh wait, hold on. And get the second element, which is the accuracy here. And we're going to multiply that accuracy by 100 because I do want to display it as a percentage. So to 2 decimal places, and that's accuracy. Just indent this up, and let's take a look. Alright, so not so good. We have about 55% accuracy, but we really can't expect too much with this small amount of data. Now, I'm sure we could probably get it up higher if we really put in the time. I'm not going to do it, but I have a hunch we could probably get better results than this. Alright, so that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.